Hello? Hello? Yeah. So I am in the scene now. Hi everybody. This is my third consecutive semester with you, and I hope that you have enjoyed the previous two semesters and you will enjoy this semester too. Anyway, so I will start with a new topic, that is geometric algorithms. You have seen a kind of analysis technique called amortization, and you have also seen graph theoretic algorithms. So I will introduce a few other algorithms in the domain of geometry. So this is also called computational geometry, or CG in short. Geometry is, I would say, one of the most ancient branches of human knowledge or human science, whatever you call. And the algorithms that we are going to study will be useful in a variety of applications, including, let's say, geometric modeling, maybe robotics, graphics, and a variety of other unrelated applications, including quantum mechanics. Anyway, so geometry is, of course, you may talk about geometry in 2 dimensions, 3 dimensions, higher than 3 dimensions. So in this course, we will restrict ourselves only to plane geometry. That is geometry of or in R square. This is typically called the Euclidean plane. To every point P in this Euclidean plane has 2 coordinates, xp, this is the x coordinate, and yp, this is the y coordinate. So P is written like x comma y, where x is the x coordinate of P, y is the y coordinate of P. Okay. Of course, we have higher dimensional geometries like 3-dimensional geometry, 4-dimensional geometry, and in general any d-dimensional geometry. But in this course, we will restrict only to plane geometry. Good. Okay. So, today I will talk about some basic objects of geometry. As I have already mentioned, a point is the first basic object specified by 2 real valued coordinates. So x and y in computers, they are usually floating point numbers. That is, you have either float or double. I will come to the implications of floating point calculations little later. Let me present a set of formulas and small algorithms for doing small things. Then we will study more serious things. The second basic object is definitely a straight line. Now, question is, how do you specify a straight line? There are many ways I can do it. So, this is one of the most conventional formats. This is the slope, M is the slope, C is the y-intercept. So, it is the slope-intercept format. Of course, this x and y are essentially placeholders. You only need to store two floating point values, the slope and the intercept, M and C. Unfortunately, this equation cannot represent a vertical line whose slope is infinity. So, this is only for non-vertical lines. You have to pay special attention like this, x equal to c, if you want to specify vertical lines. Vertical line passing through c, 0. Yeah. Now, because you have to handle this particular case in a separate manner, so this is not exactly a very, I would say, good way of representing lines. I can also do, this is the better representation, which can capture both this type of lines and this type of lines. Okay, so here of course I assume that A and B are not both 0. One of them can be 0, but they cannot be simultaneously 0, otherwise it's not an equation at all. So this is definitely better representation because it can handle arbitrary lines, vertical, horizontal, whatever. Okay. There is a third way which we also use for representing lines. And this also turns out to be perfectly general and sometimes more useful than this ax plus by plus c equal to 0 format. So, what is that? Is that a line, straight line? If I do not say anything about the straightness of the line, that line means straight line, not a curved line. So, a straight line is specified completely by two distinct points on it. Okay. If we specify 2 points, then there is a unique line, 2 different points, distinct points, then there exists a unique line passing through, unique straight line passing through those 2 given points. So, if, for example, one point is P1, having coordinate x1, y1, and the other point is P2, having coordinate x2, y2, then there are 2 ways I can represent this line. If I want to represent it in the form ax plus by plus c equal to 0, it is going to be something like this. I may make some mistake about this signs. y2 minus y1 x, x2, x1 minus x2y, possibly equal to x1 y2 minus x2 y1. So this is the equation of the line. Maybe this may be negative. I just fully do not remember. This either equal to this or plus this equal to 0. Okay. So if I want the equation of the line in the form ax plus by plus c or ax plus by equal to c, then this is it. There is another way of finding all points on the line. So that is called the parametric form. So all points on this line passing through P1 and P2 can be given by 1 minus t P1 plus t P2. So I apply this 1 minus t operation and this t multiplication by t and then addition individually on the x and y coordinates. So this means 1 minus t x1 plus t x2, 1 minus t y1 plus t y2. So any point on this line can be represented by this parameter t. Okay. And what is the value of t? Now there are important things. If I allow t to be an arbitrary real number, then I get the entire line. If I allow t to be non-negative real values, then it is the line starting from P1 passing through P2 going ad infinitum. Okay, arbitrarily in the direction P1 to P2. This is often called a ray starting at P1 and passing through P2. Finally, there is another very important range of t. If t is allowed to assume values in the closed interval 0, 1, then we say, okay, all the points that we get by putting all the values of t in this range, restricted range, this is basically the line segment P1, P2. So it's a finite thing, a straight line or a segment of it starting from P1 ending at P2. If I put t equal to 1, okay, t equal to 0, I have P1 here, this does not exist. And if I put t equal to 1, this term does not exist, this just becomes P2. So as t varies from P1 to P2, as t varies from 0 to 1, this point varies on the straight line from P1 to P2. Okay. Yeah. So that's about different line representations. There is another fundamental thing before I go to more, I would say, more complex settings. It is this. What is the distance between 2 points, P1 and P2? So the notion of distance is another important and interesting thing. So, of course, distance can be defined in many ways, but in more applications than not, we have, by distance we will mean the Euclidean distance. Okay. So basically, if P1 is equal to x1, y1 and P2 is x2, y2, the distance between P1 and P2 is nothing but the square root of x1 minus y1 square, x1 minus x2 square, y1 minus y2 square. Okay. But in general, for every positive integer k, I can talk about this distance dk p1 comma p2 is the kth root of this sum x1 minus x2 whole power k. Of course, I would make them positive by taking this absolute value here also. Here I don't need, because x1 minus x2 whole square or x2 minus x1 whole square, they are the same thing. But if k is odd, then this thing matters. Okay. In particular, if I put k equal to 1, which is nothing but this plus this is called the Manhattan distance. Okay. So there is another notion of a distance. This is d infinity p1 p2. This is basically the max of x1 minus x2 absolute value and y1 minus y2. More often than not, we will consider this distance d, which is nothing but d2. Okay. So this is nothing but d2 p1 p2. Okay. Okay. Fine. So these are all, I would say, elementary stuff. We will be doing something soon which requires us to compute angles between two lines. So let's say we have 3 points. Maybe let us call it P1, P2, P3. And I want to compute the angle maybe in counterclockwise direction. If you compute angle in the clockwise direction, then this is this. Okay. 2 pi minus this angle. Okay. So if I can compute any one of this, I can compute the other by simply subtracting that angle from 2 pi. Okay. So how to do it in constant time? So let us say this is x1, y1, this is x2, y2, this is x3, y3. Okay. First I do one thing. I give a translation of these 3 points, or for that matter the entire plane, by the quantity minus x1 minus y1. So that now P1 becomes the origin. Okay. And this simple translation is both distance preserving and angle preserving. Right. So, translate by this quantity. Okay. And then I can assume that P1 is the origin. Fine. Then, so I can now assume after this translation, this is just 0, 0, and I rename this x3 minus x1, y3 minus x1 as x3, y3, x2 minus x1, y2 minus y1 as x2, y2. Okay. Now what I do, I just compute this angle. This angle. Okay. How do I do it? So, you know that there is something called A tan 2. This will give me an angle, theta. Y3, x3. Okay, so A tan 2 is actually a math library function. If you call it, you will get the angle relative to this x-axis. Okay. Now what I will do, I will make a rotation around the origin by this angle theta. Okay. And if that thing happens, this P3, this P1, P3, this line is now lying on the, will lie on the x-axis. So I can consider this as x-axis. So how to do it? So it's easy to see that if I want to rotate by this angle theta in the counterclockwise direction, then I have to multiply every coordinate by this cos theta minus sin theta, cos theta. Okay. So if I multiply this with x3, y3, this will now go to the x coordinate. And if I apply the same thing on P2, I will get some x2 prime, y2 prime. Right. Multiply by the same transformation matrix. This is a rotation transformation. And this is also rigid because it is distance preserving. This is also, it's distance preserving and also angle preserving. So, most importantly, I do not need to multiply this by x3, y3. Instead, I would like to multiply by x2, y2 to see where this P2 translates to, rotates to. Okay. So now I have P2 somewhere rotated here, and then I make another call. If this is x2 prime, y2 prime, then I make another call, A tan 2, y3 prime, y2 prime, x2 prime, to compute this entire angle. Okay. In short, I will later argue why this can be assumed to take constant time, A tan 2. And then you have, once you have this theta, you also have to invoke cos, sin and all these functions, math library functions. You will assume all these things take constant time. You see that you can compute the angle between these two rays, P1, P3 and P1, P2. Okay. Good. Okay. Fine? Okay. So far, we are talking about lines as points going infinitely in both the directions, right? But now, if I am given a point, or if I am given a line, maybe given by 2 points, or in any of these representations, and if I am given a point, another point, okay. So, now if I ask the question, to which side of the line the point lies, then we need to introduce the concept of orientation. And this once again requires the specification of the line by 2 points on it, P1 and P2. So I have a line like this. This point is called P1. This point is called P2. On this line there are two orientations, from P1 to P2 and from P2 to P1. Okay. So now two orientations are possible. P1 to P2, and the second one is P2 to P1. Okay. And depending upon which orientation you choose, the third point, which may be here, okay. So let us think of 3 points, P, Q and R. And let us take this orientation from P1 to P2. Okay. So assume that you are moving on the line from P1 to P2 in this direction. Then P will appear to your left. R will appear to your right. Whereas Q will appear on the line itself. Okay. Soon we will, of course, and I would say, if you take the other orientation from P2 to P1, then P is to your right, R is to your left, Q is again on the line. Okay. And in the next class, we will have to resolve this issue. Given an oriented line or line segment, of course, we will also think about the line segment P1, P2 or the ray starting from P1 to P2. Okay. Q may lie inside this, outside this, but it lies on the line. Okay. In any case, in the next class itself, I will require a way how I can identify whether a point is to the left or to the right or on the line, specified by 2 points P1 to P2 with respect to, let's say, P1 to P2 orientation. Okay. So this can be done as follows. If P1 is x1, y1, P2 is x2, y2, and the third point P is x, y. It may be here, here or here. Then I simply compute this determinant side P1, P2, P 1, x1, y1, 1, x2, y2, 1, x, y. This is a 3 by 3 determinant. This is 1, these are the x coordinates, these are the y coordinates. Okay. Now I have these 3 cases. Zero, greater than 0, equal to 0. Okay, let me write more plainly. 3 cases, equal to 0, greater than 0, and less than 0. So these are 3 possibilities. And what is the relation of the point P with respect to this? It is this. This is equal to 0 if and only if P lies on P1, P2. Of course, for line, you do not require any orientation. Okay. It may lie in the segment, outside the segment, beyond P2 or before P1. Anyway, all the cases are identified by this equal to 0. And it is greater than 0 if and only if but now, of course, you require orientation. So maybe I can write it this way, P1 to P2. So, if it is positive, then P lies to the left of this, and of course you understand, now P lies to the right of the oriented line from P1 to P2. Okay. Yeah. So, this is just a 3 by 3 determinant. By calculating the determinant, you can easily identify whether it is the case like this or Q. Q was here. R was here. Okay. Which case it is. And in the next class itself, I will use this result very, I would say, extensively in many algorithms. Okay. So, given two lines, this is also required. Given two lines A1x plus B1y plus C1 equal to 0, or A2x and A2x plus B2y plus C2 equal to 0. They have an intersection point if and only if they are not parallel. And they are parallel if and only if A1 B2 minus A2 B1 equal to 0. So, of course, if this equality holds, then you cannot compute the intersection point. They are either the same line or they are parallel lines. They do not intersect in the finite plane. If this is not equal to 0, then of course you can solve these two equations. This is solve for x and y and you will get the intersection point. It's a fairly straightforward procedure, and if you convince yourself, it's almost obvious that this can be computed in O1 time, constant time. Okay. Okay, so just one more issue about straight lines. So, consider any 2 points again, P1, x1, y1 and P2, x2, y2. So, in this bi-line segment, consider this perpendicular bisector. Okay. You can find the equation of this bisector, and if I am not mistaken, this line has equation like this. Again, some of the signs may be wrong. x1 minus x2, x plus y1 minus y2, y equal to maybe this one. Okay, so just check from any book or anywhere. This may be this or the negative of this. Okay, which one is correct? I do not fully remember. and I am also not very sure. Okay, I will just check whether I am making any mistake. This is fine. This is fine. X1 square plus y square minus x2 square plus y by 2. Yeah, this is fine. Okay. Okay, good. Now, this is the equation of this perpendicular bisector. Now, it is precisely that line on which all points, take any point P on this, distance between P and P1 is equal to the distance between P and P2. Okay. On the other hand, if I consider all, okay, so this line actually bisects the entire two-dimensional plane into two half planes, right? This side, which contains P1, here all the points satisfied D, P, P1 less than D, P, P2. Whereas on the other half plane, here, if I take any point, I have D, P, P1 greater than D, P, P2. Okay. In the last topic that we will cover in this section, we have to use this. So, this half plane will be called H12, points that are closer to 1 than to 2. And this half plane will be called H21, closer to 2 than to 1. Okay. So, in the study Voronoi diagrams, we have to use these notations and understanding. Okay. Okay. So, I believe that's all about lines that I wanted to mention. We need another important thing. These are called polygons. Okay. So starting from triangles, rectangles, different types of rectangles, we know these are all called polygons. A set of things like this. Okay. And polygons are specified by a set of points P1, P2, Pn. This is called an n-gon because there are n corners. So whenever I specify this sequence is important. From P1 you go to P2, then go to P3 and so on until you go to Pn and come back to P1. Okay. Now, there are polygons of different types. First, simple, not simple. A polygon is called simple if its edges, which are actually line segments, not full lines, do not intersect except perhaps at the end point. Okay. So, the edges okay. Whereas, if we allow edges to intersect like this, this is not a simple polygon. Okay. So, edges are allowed to intersect. This one intersect. This one and this one intersect, but this intersection point is not a corner. Okay. So, Non-simple polygons are usually not things that we will study. We will study only simple polygons. Okay, so this is this. And if you are given a simple polygon like this, you see that if you remove that polygon, I mean this, just the boundary of the polygon from the Euclidean space, you will be left with two pieces. There is one bounded space like this inside, okay, and there will be an unbounded space which is the outside. So this inside is called the interior, and the outside is called maybe exterior or whatever. Okay. Now, given a non-simple polygon, there is a question of interior and exterior. If I remove this from the two-dimensional plane, I will be left with many pieces, possibly, right? This piece I will have, this piece I will have, this piece I will have, this piece I will have. So, the concept of interior and exterior is not a well-defined one for non-simple polygons, but if I have a simple polygon, its removal leaves the interior, which is a finite amount of space, and the exterior, which is an infinite amount of space. Okay. Like I would say lines, I can give an orientation to any simple polygon. Okay. Again, simple polygon only. So, one is this, other one is this. There are two orientations. For a simple polygon, how do I distinguish? If I take this orientation, this. Of course, I cannot talk about the orientation being clockwise or counterclockwise, because if you see, here you are moving in the clockwise direction, whereas here you are moving in the counterclockwise direction. Okay. So, by using this analogy of counterclockwise and clockwise, I cannot classify these two orientations. How do I classify? If I move along this direction, then the interior will always lie to my right. Right? Okay, if I move. On the other hand, if I take this direction, this orientation, then the interior will always stay to my left. So that way I can specify two orientations. Okay. If I move along the boundary, whether the interior lies to my left or to my right. Okay. So simple polygons can be oriented. Okay. The special case of simple polygons is what we will start studying from the next class. Is called convex. Of course, I can also talk about convex regions, but to start with, we will study what is called convex polygons. Okay. In particular, we will study what is called convex halves, which are actually convex polygons. Okay. So, a polygon, or for that matter any region, is called convex if I take any P1. So, let R, okay, let R be a region in the two-dimensional plane. Okay. This is called convex if I take any two different points P1 and P2 in R for any points P1, P2 in R, the entire line segment lies in R. That is, if I consider the parametric equation of the line segment, t is restricted to closed interval 0, 1. For all these values of t, I will get different points, they will all belong to R. And a polygon is called convex if its interior is a convex region. Okay. Interior plus you may also consider its boundary. Okay. So everything outside its exterior, that is a convex region. Okay. So here is an example of a convex polygon. Okay. Take any 2 points here and here. This entire line segment lies on it. You may also take 1 point here, another point here. This entire line segment joining this lies inside. On the other hand, that picture that I drew, this region or this polygon is not convex because, for example, if I take a point here and a point here, join them by a line segment, so some part of the line segment goes outside the polygon. So this is convex, this is not. Okay. So we will soon work with convex polygons, and again we may make some kind of, I would say, assumption that we will take the so-called right orientation. That is, I will start from any point and traverse in such a direction that the interior always stays to my right. If I am dealing with a convex polygon, then this is basically the clockwise orientation. For a convex region or for a convex polygon, definitely I can talk about clockwise and anti-clockwise. Clockwise is the same as the region interior being to my right. Anti-clockwise or counterclockwise means the interior is to my left. Okay, so clockwise and counterclockwise make sense when I talk about convex polygons or regions. Not here. This is counterclockwise, clockwise. Right? Again counterclockwise, clockwise. Okay. But the left-right orientation thing, that can be applied to this non-convex region also. Okay. Okay. So we will typically assume that I will specify convex polygons by starting at some point and moving in the clockwise direction, so that the interior is always to my right. Okay. Okay. Convex polygons. This is something we will study in the next class. I would stop after talking about a couple of general matters. The first one that I already mentioned once, floating point calculations. What are the implications of this? Since we are talking about floating point computations, one thing is clear, that all calculations, or I would say more often than not, calculations are approximate, not exact. Okay. For example, even if I consider, a very simple thing like taking the distance, Euclidean distance of 2 points, then again I have to take square roots. In general, you are not dealing with Pythagorean triples, and therefore the final value will be a floating point value. Okay. it's not even rational. In any case, so this means you are doing only approximate calculations. What does it mean? This means that however hard you try, there will always be some little bit of error in your calculated value. And if it happens only once, it's 10 power minus 15, nobody cares, right? You usually do not require things with more precision. But still, if it happens that these approximation errors keep on piling together, if you do some kind of iterative programming, a small error in one step affects or introduces more and more errors in further future steps, then eventually these errors may pile up to give you something very, very different. I mean, very approximate, very wrong, in fact. And I do not know whether you are already familiar with this thing. Numerical stability. So if you do approximate calculations using floating point numbers, you have to accept errors and should avoid situations where errors should not pile up to eventually give a huge amount of error. So your algorithms, if you want to implement, should be numerically stable. Okay. It is unstable if a situation like that occurs. Small errors eventually pile up to big error, giving unacceptably poor result. So, numerical stability is an issue when we talk about geometric algorithms. Actually, they are implementations. Okay. But in this course, maybe we will have a programming assignment on geometric algorithms. In that case, stability may be an issue. But when we study computational geometry algorithmically, we will not bother about numerical stability. Okay. And second thing is that we are already familiar with applications of these things in computational geometry, like arctan, tan inverse, sine, cos. We will also have to use square root if you want to compute distances, Euclidean distances between points. These are all math library functions. Okay. So what should I assume about their running time? It's not a basic operation like addition, subtraction, multiplication, quotient, remainder. Okay, or bitwise operation like OR, XOR, AND. Right. So what are their running times? That's an important issue. So what we typically do, so you know, a float has 23-bit precision. Okay, mantissa. Whereas a double, if I am not very much mistaken, it's around 52, 51. I think 52 is correct. It's a 52-bit precision. So most, if not all, of these, I would say, math library functions are iterative functions. They start with some initial value of the output and iterates over this value, reducing the error more and more until the error is so small that it is safe to return that value. So, whether it is arctan 2, sine, cos, tan, square root, they will work and will stop as soon as an accuracy of 23 bits or 52 bits is achieved. Okay. Now this 23 and 52 are constants. Okay. And depending upon which algorithm they use, it may require 23 iterations, 52 iterations to achieve that accuracy, provided that this convergence is linear. And in each iteration, you do some constant number of addition, subtraction, multiplication, division, things like that. In any case, since this 23 and 52 are finite, we will assume that each of these a tan 2 sine cos square root take 1 running time. Okay. So that's a constant thing, not necessarily 1 clock cycle or something like that. It will be 1000 clock cycles, 100 clock cycles, but still we will assume that this will take 1 running time. In particular, when I talk about the input size for a geometric algorithm, it's typically the number of points that is input, number of corners of a polygon, that kind of thing. So that number is n, and that n, the running time, this running time of these have nothing to do with that input size n. So we will always assume that this math library functions return in constant time. Not necessarily very fast, but constant after all, O1. Yeah, so that's about floating point things. Before stopping today, I just introduce a last general terminology. Subjects in general position. For example, we may talk about points in general positions, lines in general positions, points and lines in general positions, points and circles in general position, only circles in general position, things like that. Now, what does this really mean? Actually, the meaning of these general positions is very much context dependent. When we talk about points in general position, we may mean one or more of these things. No two points at the same x coordinate. It may also mean no two of the given points have the same y coordinate. Okay, it may also mean that no three are collinear. Okay. Depending upon the context, it may mean many other things. Okay. And similarly, when I talk about lines in general position, this may mean, depending upon the context, no two are parallel to each other. Again, the situation may so demand that no two, okay, no line is parallel to x or y axis, It may mean this. Some algorithms require this assumption for lines in general positions. No three are concurrent. Okay. And it may mean more things depending upon the context. So, algorithms are typically specified for objects in general position. Okay. And if you build your collection of points or lines or other objects, let's say randomly, okay, it is with high probability that they will be in general position. Okay. But of course, in real life situations, objects are not necessarily in general positions. For example, if a robot wants to move from one point to another point inside a room, the room is typically assumed to be a square, right? And the objects that you have, like let's say a table, some chairs, they are usually kept aligned with respect to the walls, right? So in real life, objects are not necessarily in general position, but if we consider randomly generated points or lines or objects, they may be assumed to be in the general position. Okay, and then you design your algorithm for these objects in general position. And then there is another term. If the objects are not in general position, they are called degenerate. Okay. If some objects are not, if the points are not in general position, they are called degenerate. So it's a very common practice in computational geometry. So design an algorithm for a given problem for objects in general position. So this algorithm is usually the simplest form of this design. And then if you know that your real life instances will have degeneracy, so you just modify your algorithm to handle degeneracy. Okay. So instead of, I would say, bothering too much about degeneracy in the first step itself, we assume points or lines or objects are in general position and first have some algorithm ready. And then if I want to introduce some degenerate cases which are not handled by the first algorithm, okay, which are meant for general position, then we just make some small changes, small tunings, so that the algorithm can now handle degeneracy. One or more types of degeneracy. Maybe during this course of this lectures on computational geometry, we will see one or two examples where it is possible to have degenerate cases. Okay, so I think I should stop at this point. I have not essentially covered anything substantial or I would say meaningful towards geometric computations, but only set up some notations and some basic things. So in the next class, in the next lecture, I will start exposition to convex house. Good. So let me stop for now. Okay. See you again in the next class. Bye.